This tutorial is going to be on conducting a one-way ANOVA in SPSS, and I'm just going to use the example from the textbook. So in this example, what we have are 30 children that have been randomly assigned into one of three groups, and each group got a different type of chili sauce made from a different chili. So we've got the poblano group, the jalapeno group, and the habanero group. And so these peppers are, there's a difference in how hot they are. So poblano is the less hot, medium hotness, and then the habanero is the hottest pepper. So this sauce that they got differs in heat. And then the dependent variable is the time in seconds it took before each of the children had what the authors call a volcanic eruption, which we'll just say that they maybe spit it out. They spit out the sauce. So we've got time in seconds. So you will have similar data for your lab assignment, but it is different data. So the tutorial is going to be the practice exercise on page 116. And so it's the same groups. So there's chili groups, but then you've got a different dependent variable. So make sure that you're not using this data, you use the data that appears in the table on page 116. It's also the case that the way that the textbook presents the data, both in the practice exercise as well as earlier in the chapter, they actually have a table with 3 columns, and so each of the groups is its own column. Notice the setup in SPSS, however. We only have 2 columns of data, so we have 2 different variables. We've got our grouping variable, which is our independent variable, and then we've got our dependent variable, which is our scale variable in the language of SPSS. So recall that in order to do this, we have to go to the variable view. I've set up this nominal categorical variable, which is our group variable, and then our scale variable, which is the DV. I've also had to go in, and you'll have to do this as well, is set up your values and your labels for each of your groups. All right, so that's just an important thing that I wanted to mention, is that the data are displayed just a little bit differently in various places in the textbook and for sure in the practice exercise. So you need to set it up in this 2-column format where we've got a grouping variable and then this scale variable or an independent variable and a dependent variable. And then, I'm just going to toggle back and forth here, but you can clearly see that I've got the values set up to represent each of the categories of that grouping variable. All right, so more generally, when do we run a one-way ANOVA? We do this when we have at least 2 groups, but typically when we have 3 or more groups, because when we have 2 groups, we typically do a t-test. But we can do an ANOVA with 2 groups. But so anytime we have 2 or more groups and we want to compare mean differences between those groups, we can do an analysis of variance. An analysis of variance really tests a null hypothesis that each of the means from the groups, the sample means, are sampled from populations that have identical means. Okay, so we're testing a null hypothesis that these means are sampled from populations that have identical means. The analysis of variance is known as an overall or an omnibus test. The statistic that this analysis produces and that we're going to look at in SPSS is called an F statistic. It's called an omnibus test because the question that it can answer is whether or not the means come from populations that have identical means or no, they don't. And so that's it. So what we're able to test is whether the sample means differ meaningfully, whether there is a meaningful or significant difference between the means, or whether there is not. If and when we find a statistically significant difference, we then have to do follow-up analyses to determine which of those means are statistically significantly different from one another. And so there's actually two ways of doing this. The textbook presents something that are called post-hoc analyses. So that's basically Latin for after the, I don't know what the exact Latin translation is, sorry, but it basically means after the fact. So after the fact, or after we find a significant F statistic, sometimes called the F ratio, there are different follow-up tests that we can do to probe for differences between the means. So those are after the fact. There's another set of analyses that we can do to follow up a significant F test, but these are planned in advance. So these are called planned comparisons or sometimes planned contrasts. The difference is whether we have a specific hypothesis ahead of time about the relationship between the means from our different groups. So if we predict ahead of time, as a for example, that Poblano and Habanero will be different, okay, that those means will be meaningfully different, if we get our overall F statistic and if that is significant, we can then follow up using a planned contrast. If, on the other hand, we do not have what is called an a priori or ahead of time hypothesis, we only hypothesize that the means will be different in some way, but we don't specify which mean will be different from another, we will do a post-hoc analysis, as I'll demonstrate here. So I'm essentially, the textbook doesn't show you this and I don't show you this. I don't show you what to do if you have a prediction ahead of time about the specific relationships between means. This is only a way to kind of probe after the fact. All right. So let's get into it. So we've got the setup. We're just going to go to our Analyze menu and then our Compare Means menu. So we've been working in our Compare Means menu for the last several lab assignments and tutorial. So mostly we've been doing t-tests up until this point. So we're going to do a one-way ANOVA. And there's many reasons why we do a one-way ANOVA instead of multiple t-tests, but the main reason is in a single analysis, we can test for differences. Whereas if we'd have to do multiple t-tests to compare to compare each group to one another. So we'd have to do 3 different t-tests. So it's not only more efficient to do a one-way ANOVA, but actually more importantly, we minimize the chances of making what is known as a type 1 error, that is rejecting the null when we should not. So every time you do a statistical analysis, we typically set the alpha, or the type 1 error rate, at 0.05. Okay, so that's our significance level. So we set our significance level at 0.05, and by doing one test, that is our chance of making a wrong decision. That's our error rate. If we do 3 t-tests, we've got that 0.05, or we've got that 5% error rate each time we do the test. So this is importantly a way to minimize the chances of making a type 1 error. So we do a one-way ANOVA. Okay, I said we're getting into it, so here we go, we'll get into it. So in our dependent list, this is where we will enter any dependent variables of interest. It turns out that we only have 1, so we'll just move that over. But this is just to say you can do an analysis of variance for several dependent variables at the same time, if you want. In the language of analysis of variance, our independent variable is actually called a factor. So you'll see that word there, factor. Okay, so this contrast tab is what I was referring to before. If we had a hypothesis ahead of time, we could go in and specify which groups we want to compare to each group. But we don't, so for our purposes in this class, we're going to ignore this contrasts button. What we are going to select is a post-hoc test. Now you'll see all the different choices in here. There's many different types of post-hoc analyses that have been developed. If you take an advanced statistics class, you'll learn all the differences and the nuances between them. In short, what they try to do is give you the best possible chance of finding a real effect when a real effect exists. So that's the concept known as statistical power, while at the same time being a slightly more conservative test than just running a regular old t-test. Okay, so running a regular old t-test might be, well, why don't we, if we get a significant F ratio, why don't we just do the 3 possible t-tests? The issue there is because you have the chance of making a type 1 error every time you do the test. So what post hoc test tries to do is minimize the chances of making a type 1 error. So they end up being just a little bit more conservative, meaning that it ends up being a little bit more difficult to find statistical significance when using a post hoc test than when using a regular independent samples t-test. And just how kind of stringent or conservative the test is will depend on how the test was developed. So there's all types of different situations in which you would use one versus another. So for instance, the Chaffee is the most conservative test. But for our purposes, we're just going to select the LSD test, which is not named after the drug, unfortunately, but it is named after Fisher's least significant difference. The textbook goes through the formula for how that's calculated. Really don't worry about it. Don't worry about the formula at all. We're just going to be, in fact, they didn't get that formula right, which is just a side note, which is crazy to me. But anyway, we're just going to interpret the output. So select LSD, our first option here. And if you want to select more, just for funsies, you can go ahead and do that, but just select LSD for the tutorial. Okay, and I just hit continue. The other option I'm going to select, very important, is to get your descriptive statistics. Your descriptive statistics are produced automatically when doing a t-test, but you actually have to select it when doing analysis of variance. So again, go into options and then click descriptives. And then the other thing that we're going to do is get a means plot. Now, all kinds of fancy tests here. When you get into advanced stats class, you'll learn about these. But for our intro stats class here, the only option we're going to select is descriptive statistics, and then we're going to get a means plot. And we'll continue. And then if you wish, that's all we have to do. I've talked about this bootstrap feature before. We don't do it. We've also got the option to estimate effect sizes. Not even going to worry about that as well. So we're going to keep it very, very simple. Okay, you can paste that, or I'll just click OK. In fact, you'll need to paste it for your tutorial, but I'm just going to click OK. All right, so here's our output. So here's our table of descriptive statistics. We're pretty used to looking at this right now, but we've got our sample size for each group. We've got the mean for each group, standard deviation. Notice that it's the same. That's not a coincidence. That's the textbook authors in this example just decided to make the standard deviation the same. You get the standard error of the mean, the confidence interval around the mean, you get the minimum and the maximum. So this is really, it's always important to look at your descriptive statistics because this gives you a sense of the relationships among the groups just right away. Now, I've tried to stress this, but I'll stress it again. In statistics, we never do an eyeball test. We never just look at those means, okay, these are sample means, and look at them and say, oh, okay, well, there's a difference there, so they must be different. Well, yes, they're different. 14 is different than 12, and 12 is different than 9, and 9 is different than 14. But are they meaningfully different? Are they statistically significantly different? What we have to say to ourselves is, even if the null hypothesis is true, the null hypothesis being that these groups are sampled from populations that have identical means, just because of sampling error, there's bound to be some difference between those means just due to pure randomness, just due to chance, just due to sampling error. So it shouldn't be surprising at all that we see differences among the sample means. But that's never what our hypothesis is about. Our hypothesis is always about differences between population means. So what we're really testing is, are these differences big enough? Is there a meaningful enough difference to reject the null hypothesis that these groups are sampled from populations that have identical means in the population. So if these differences are big enough, if they're meaningful enough, then we can reject that null hypothesis. So it's never a test of whether these sample means are different, because they are, but it's whether they are statistically significantly different or meaningfully different enough to conclude that the population means are different. Okay, so in statistics class, you will learn how to calculate the F ratio by hand. Some of you may have at this point in the semester, some of you may have not. For our purposes, we're just going to go straight to this F statistic or F ratio, and know that it's essentially calculated as taking two statistics called a mean square between and a mean square within, and dividing the mean square between by the mean square within. That gives us our F statistic or the F ratio. The mean squares are essentially two different approaches to calculating variance. Under the null hypothesis, if these groups come from populations with identical means, we should get roughly equivalent measures of variance when estimated using a between groups approach as well as a within groups approach. Anytime we get an estimate of variance, the variance between the means, that is much larger than the estimate of the variance within the groups, we'll get an F ratio that is big, and that signals that there is more variance, that is more difference between the sample means than would be expected simply due to random chance or sampling error. Okay? So we're going to evaluate that F statistic. In stats class, you evaluate that F statistic against a critical value of F. Using SPSS, we simply just look at our significance value. And that tells us whether our F ratio is big enough to be considered statistically significant. So we're looking for a significance value here that is something something that is less than, the prof almost messed it up, goodness, something that is less than or equal to 0.05. So clearly here our significance level is below that 0.05 threshold. So we know that we do have significant differences between the means, or we can reject the null hypothesis that the means in the population are equal. What this overall F statistic doesn't tell us is which mean is different from which other mean. Okay? Again, it is an overall, or sometimes called omnibus test, and the F ratio alone does not tell us which mean is meaningfully different from the others. That's why we do the post hoc analysis. So here we have the results of our Fisher's LSD test. So in this table, there's quite a few numbers, and a lot of the numbers are redundant. So I'll walk you through it. So in our first row, basically using the language of the textbook authors, we've got kind of the major row and then the minor rows. We can just say that we've got rows within rows. Doesn't matter. Okay. But what we've got are all of our different comparisons. So we've got here in this first row, we've got our poblano group compared to the jalapeno group, and we've got our poblano group compared to the habanero group. This first column is the mean difference. So we see a mean difference here of 2, which makes sense because if we go up to our descriptive statistics, we see that poblano was 14 and jalapeno was 2. So we've got a mean difference of 2 because we're taking I minus j, so I minus j, 14 minus 12 is 2. And now what we're going to do is we're going to look at the statistical significance of that mean difference. And same as always, we're looking for that threshold of 0.05. Do we have a significance level that is less than 0.05? Here we have a significance level of 0.095, so this is greater than 0.05. So we do not have a statistically significant difference based on this test between poblano and habanero. Okay, so 14 and 12, there is a difference here, like 14 is different than 12, clearly, but it is not a meaningful difference. What that means is that this is not a sufficiently big difference to conclude that the means in the population are different. what this means, this is telling us, is that the difference between 14 and 12 can just merely be due to sampling error. Like, it's possible that if we were to give everybody in the population, everybody in the world, these two different chili sauces, that we would see an equivalent eruption time. That's a possibility. Right now, our test is, we have insufficient data to rule out the null hypothesis, which is that the population means are the same. All right, so 14 and 12, while different, they're not meaningfully different enough to rule out the null hypothesis, okay, that the means are the same. Okay, so that's based on this evaluation of statistical significance not being less than 0.05. So this is a not significant result. On the other hand, we have Poblano versus Habanero. Here we see a mean difference of 5. Okay, we got that difference of 5 by taking 14 minus 9. And this is a statistically significant difference because the significance level is less than 0.05. The significance is not 0.00. It is just something 0.000. It is just something less than 0.001. SPSS had to round off. So there's never a probability of 0. Never a probability of 0. It's just a rounding off. Okay, so that's two of our comparisons. Poblano versus Habanero, Poblano versus Jalapeno, Poblano versus Habanero. What you'll notice here is that we've got a redundant comparison. So we already did jalapeno, poblano, poblano, jalapeno, but we've got it again here. Okay, you'll notice that the difference is the same, just negative. That's because the numerator, basically, of the formula is just different. The comparison we haven't yet done is jalapeno versus habanero. That's a difference of 3, which we got from 12 minus 9. And that mean difference is sufficiently big to be statistically significant. All right. So what can we conclude from these data? We can conclude that people that eat poblano peppers erupt significantly slower than people that eat habanero peppers, and people that eat jalapeno peppers also erupt significantly slower than people that eat habanero peppers. However, there is not a meaningful difference between poblano and jalapeno, or we could say the results of the study, the most precise way is that the results of this study are inconclusive to establish that there's a difference between the eruption time of poblano and jalapeno. Okay, so and then we can just go down to the means plot, and here we've got, again, this is kind of a curious choice for SPSS. A bar chart would be more appropriate than a line chart, given that we have a categorical independent variable. But here we've just got the mean of eruption time plotted. So we've got the 14 seconds, the 12 seconds, and then the 9 seconds. And so we've just got a plot there. You can also, if you want, go into graphs and you can produce a bar chart of these means. We learned how to do that in previous tutorials, but this is one way, just to get a graphical representation, to get another look at the data. And again, essentially what we've established is that poblano, different from habanero, habanero also different from jalapeno, but not a big enough difference between poblano and jalapeno to establish that these two means are different in the population. All right. Hopefully you found that helpful. It's a good kind of conceptual background, and it'll kind of get you started on doing the tutorial as well. All right. Thanks for watching.